Okay, so those of you watching at home, we're on page 40 to 47 of the PDF. That's a different page number if you're looking at the Active Teach version. So those things on the printout, I would call those networks. They're referred to as graphs, and this has a whole range of terminology that we need to be comfortable and familiar with. And you can tell how sort of old-fashioned I am. So when I look at those sorts of networks, I think about nodes and arcs. They are also known as vertices and edges. So vertices and nodes are just the places in the network. And edges or arcs, they are the roads joining the places. Except, of course, this doesn't have to be a road network. It might be the cost of sending data between particular places. And these graphs do not have any numbers on them, but sometimes you do get graphs with numbers on them. Those are called weighted graphs or weighted networks. And we're going to be dealing with mostly those. So rather sort of claw through this, I'm going to just encourage you to spend a bit of time independently getting the terms. So I don't know if you want to star the ones that I think are really important. So we've got vertices and nodes, which are the places, edges and arcs, which are the roads. It then talks about the degree or valency or order. I mean, how maths is this? We don't have one way of describing something, we have three ways of describing something. And the order of a node, or the degree of a node, or the valency of a node, or the order of a vertice, or the degree of a vertice, or a vertice, or the valency of a vertice, all six of which mean the same thing, are how many roads meet at that point. How many roads meet at that point. And nodes can be odd or even. They are odd if their order is an odd number and there is an odd number of paths that meet at that particular place, and they are even if there's an even number. But because each road, when you have a network, gets counted twice, here and here in the orders, the sum of the orders has to be an even number. Has to be an even number. So if you add up all of the orders of the nodes in a network, that's got to be an even number, because every edge within that network is counted here in the order of that node and here in the order of that node. And this presents us with the opportunity to answer some questions. So, for example, here is a question. There we go. Right, so a graph, that's a network as I think of it, has 5 nodes and 8 edges. And the valences, the orders of the nodes are x minus 1, x plus 1, 2x minus 1, and x minus 1. Find the value of x. So what we're talking about is a network where there are 8 of these. So that should tell you something about what the sum of the orders is and allow you to solve that problem. Go on, have a go. Have a go. So 8 edges, each edge gets counted twice in the sum of the orders. Yeah.
Right.
So that means the orders are going to add up to 16.
Yeah, it's a
Yeah.
16.
Yeah. That's
What's the variance?
same as the order. How many edges meet at a particular node? So because we've got 8 edges, we are dealing with a situation where the orders of the nodes, why on earth we don't just use the same word all the time, I don't know, will add up to 16, because each edge gets counted twice when we're adding up the orders, gets counted here and here. And we have sort of come across this issue before, when we talked about the product rule for counting. So do you remember the sort of problem where you've got 6 people and everyone's going to shake hands with everyone else? So, you know, here's the 6 people. I'm already regretting having 6 people. I should have had fewer than 6 people. So, you know, Thurston shakes hands with 5 people. And Lila shakes hands with 5 people. And Jake shakes hands with 5 people. So the number of handshakes, so they're all shaking hands with 5 people, and the number of handshakes surely then is 30, except it's not, is it? So why is the number of handshakes not 30?
Because you won't shake your own hand, and once someone shakes one person's hand, you take it down to be 6 by 4.
Yeah. So we have to divide by 2, because that way we've counted all of the handshakes twice, haven't we? We've counted Thurston shaking Lila's hand, but also Lila shaking Thurston's hand, which they don't need to do if they've already... So that's a bit like saying, if you add up all the orders, does that give you the number of edges? Well, it doesn't. It gives you double the number of edges, because you've counted each arc twice. And that principle of the number of edges, so the sum of the orders is even, and it is equal to 2 times the number of edges. That was first sort of formalised by a mathematician called Euler, a Swiss mathematician called Euler, and it's called Euler's handshaking. And here's a new word, lemma, which is just like a sort of theory. So the sum of the valencies, stroke orders, stroke degrees is even, and it's equal to 2 times the number of edges. And that also means that if in this network I've got 1, 2, 3, 4, 5, that node has got an order of 5, somewhere else in the network there must be another odd node. That's an odd node, its order is odd. There must be another odd node to go with it, at least one, because the total has to be even. So odd nodes come in pairs in a network like this. Odd nodes come in pairs. That's sort of part of Euler's handshaking lemma. The sum of the orders is even, it's 2 times the number of edges, and odd nodes come in pairs. When you add up a list of numbers, the total can't be even if you've got an odd number on its own. So odd nodes have to come in pairs. Right. Returning to my sheet, you've got a whole load of different terms there. Trail, cycle, Hamiltonian cycle, walk, path. We'll get used to those. I wouldn't worry too much about those. But the next key terms I want us to understand are the idea of a connected graph or network. And that's where everything's connected. So we feel a little bit today like we're not a connected class because we've got poor Gooch at the back there on his own, you know. I mean, but so, you know, so a connected graph is one where all of the nodes are connected, not necessarily to all the other nodes, but in those 2 examples here, you know, H is connected. It's only connected to G, but if you're at F, you can get to H, you just have to go through G. So a connected graph, that's an important term. A loop is a term you need to understand, and that's just an edge that starts and finishes at the same place. And a simple graph is a graph where there aren't any loops. So we've got a connected graph and a simple graph. We've then got, is it on the next page? Oh, it isn't, right. So the next, in addition to those terms there, we've got connected and simple. Complete. A complete graph is one where every node is connected to every other node. Okay? So you've got... So we've got connected, simple, simple means no loops, and complete, we need to understand all of those. It is an awful waste of resources to make a complete network. You don't need to. In the old days, if you wanted to connect a town with telephone wires, you did need a wire going from point to point. That's how the first sort of telephone calls were made. But eventually they developed the idea of an exchange, so you didn't actually need to have a complete graph. You just needed to be connected. And a network like Ethernet is a good example of that. If you are connected to an Ethernet network, doesn't mean you are connected to every other computer in the network. It just means there is a route that gets you from one to the other. We've got then the idea of a weighted graph where arcs have a value, and this is where we're coming to really. And then we've also got the idea of a directed graph where you can only travel along certain arcs in a particular direction. So a weighted graph, and they are defined somewhere on this sheet. So directed graph is over the page. It doesn't say weighted graph, but there we go. So can I get you to have a look at exercise 2b, which is on the there. So exercise 2b, and just see if you can draw graphs that follow those particular conditions. So 1a, a connected graph with one vertex of degree 4 and 4 vertices of degree 1. So that means you've got 5 places. Connected graph, remember, means you can get everywhere, not necessarily directly. And then have a look at question 2. Which of those graphs are not simple? So this, for those at home, it's on page 37, the two questions we're doing, question 1 and 2. Yeah, so 1b, I did that with a loop. Because connected, you can have loops. Remember, a simple graph is one without loops. A connected graph, you can have loops. You've just got to be able to get everywhere. Has anyone done 1b differently? This one is 1, 2, 3. It's, so how did you do your...
Just do a square. Just a square.
Right, okay. Ding, 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 ding. Yeah. Nothing wrong with mine. Third one, 2 vertices of degree 2. 2, 3. Shall we, so yeah, I mean, I'm sure those aren't unique solutions. So the first one we had, this has got an order of 4, and then that's got order of 1, 1, 1, 1, and as Euler said, the odd nodes come in pairs. Here I've got 2, 2, 2, 1, and 3, and again, odd nodes come in pairs. That's 2, 2, 2, 3, and 1 as well. And C, 2 of 2, 2 of 3, and 1 of 4. And sorry, yes.
1b is the loop not worth only 1?
No, so the loop is worth 2.
Oh,
So that's, yeah, so when you, basically it's how many roads are leaving. So, you know, you've got one leaving there, one leaving there, one leaving. Just so happens that this one is, but you know, that's an order of 3. And then which graphs are not simple? So A is not simple. There are 2 edges connecting C with D. Oh no, that's interesting. I didn't add that in my definition of simple, did I? I just said no loops. So let's make that clear. Where is the definition of simple?
I think it's 1 edge.
Right, yeah, so there's only one route between any pair of, so I apologise for that. So my definition of simple is no loops plus only one way of getting between so there we go, that's that. So A isn't simple. B and C both simple, and D has got a classic sort of loop on it, so that's not simple. Okay, try not to look at the back of the sheet because it spoils the surprise. One way of displaying a network is with a matrix. So here we've got a graph. Remember, the word graph I think of it as a network because, I'm thinking of, Google Maps and directions, and the sort of algorithms we're getting into are exactly the sort of algorithms that that we'll use. So here we've got a network with 1, 2, 3, 4, 5, 6 nodes. So we can show that on a matrix. It's not really a matrix in the way that we have been using recently, but it's more of a sort of two-way table. So firstly, we've got what's called an adjacency matrix, which is just saying, whether two nodes are joined or not. So obviously A and A, it doesn't really count. A to B, yes, that is joined, but A to C is not joined. And the graph will be, and in fact, actually, I've just looked at the example, they put a 0 there. And there will be a symmetry to that, won't there? Because if A is not joined to B, then if A is joined to B, then B is joined to A. If A is not joined to C, then C is not joined to A. So just see if you can draw the adjacency matrix for that graph. It's not as bad as it looks, because once you've done, one diagonal half, the rest of it is easy. Yes.
Would that for that not be walks at a loop?
Oh. Thank you very much. Now hang on a minute.
There might be 2.
It's 2, isn't it? Yeah. There are 2 connections from F, which end at F. So yeah, that's. So yeah, we're recording the orders, aren't we? So we must have so B to E, for example, will have a 2, won't it? It's not the orders, because C has an order of 3, but that will be recorded as 3 1s. But where you've got B and E, that's going to be a 2, and that means it's not a simple graph because you've got that redundancy built in. Okay, that's an adjacency matrix. The other sort of matrix then are, and the vast majority of graphs that we meet, and they've thrown in the word network here, will be like this. This is a weighted graph where we're not just talking about joins between places, but these places have a weight. That might be a distance, it might be the cost or the time it takes to send packets through a network between those two places. So what we can now do for this mercifully slightly smaller network is we can, rather than just having the number of connections, we can have the weight of the connections. So go on, see if you can do a matrix for those two.
What if there's two connections, you just add them up?
Well, that's a really good question. I don't think you'd be, I think you'd only be expected to do a distance matrix for a simple graph where that isn't the case. Yeah, that's a good question. And they do put dashes here with a distance matrix. So A to A. I suppose you could put the 0, couldn't you? Of course, each distance will appear twice, won't it? So C to A to C, both 18. Now you can get from C to E, but there's not a direct connection, so we don't put, 36 in there. We just put the direct connections. So that's not connected. That's 19. That's 20. 16. Now, let's imagine that we've got these 5 places, and we've worked out that if we were to build roads between those 5 places, these are the distances. And what we want to do is we want to connect these places in the most efficient way. What we want to do is, so these roads aren't built yet, it's just the theoretical cost, the theoretical distance. What we want to do is design a tree. So a tree, it's one of the definitions there. A tree is a connected graph with no cycles, and a cycle is another one of the terms there, which is a route through a network that starts and finishes at the same point. What we're dealing with here when we talk about a tree is just enough edges to connect the network without any redundancy built in. Now I've got 5 nodes, 5 vertices in my network. How many roads am I going to have to build? How many roads am I going to have to build to make a tree? You're right, it's 4. It's n minus 1. So to make a tree, you always need n minus 1 edges, where n is the number of nodes. But there are plenty of ways we could draw a tree. How do we draw the most efficient tree? Well, that sounds like a sort of problem where we need an algorithm. Let me introduce you very briefly to the first algorithm that allows us to create the most efficient tree. It's a Russian mathematician called Kruscal, and his algorithm allows you to create what's called a minimum spanning tree. So a tree is just, with this network, 4 edges that connect that graph with no cycles. A minimum spanning tree is the most efficient way of doing it, and you can only do that if you've got a weighted graph. And Kruskal's algorithm just goes like this. Pick the shortest route. Pick the shortest edge in the network. So the shortest edge in the network is B to C, which is 15. And then you pick the next shortest that doesn't create a cycle with the ones you've already created. Okay? And then you pick the next shortest that doesn't create a cycle with the ones you've already created. And you continue until you've got n-1 edges. So go on, just very quickly, see if you can design the minimum spanning tree for that network using Kruskal's algorithm. It's not really an algorithm like double sort and quick sort in that, you know, it's sort of common sense if you like, but you pick the nodes in order, starting with the shortest, unless the next shortest creates a cycle with the ones you've already got, in which case you skip to the next one after that. As you build a network using Kruskal's algorithm, it's not necessarily connected. So my next choice, for example, will be D to E, which is here. So as you build it, it won't necessarily be connected.
I don't think it matters.
So what's it?
If you do E, D, C, D, A, you get the same results if you do E, D, B, C, A.
Yeah. I think in this case, it's very straightforward, isn't it? So the next one I want to pick is A to C. That's the next shortest, but that will create a cycle. A cycle, remember, is a route through a network that starts and finishes at the same point. So I'm not going to pick A to C as the next one. I'm going to skip on to the next one, which is B to D, which is 19. And then I stop, because I've hit n-1. So Kruskal's algorithm is one way of creating a minimum spanning tree, and it works by sorting the edges within the network, so we need an algorithm to do that, I suppose, but then picking them in order, skipping any that create a network. So what have we got? We've got 31, 58, so is that 77 as our... A bit too quick. 31. Oh, no, sorry. 67. So we'll do a. So actually, you could probably do page 56, exercise 3A. I think that's just on Kruskal's algorithm. So most of these terms we'll get used to using as we go through this particular work, but it is worth just reading through that and making sure you're not super sort of unaware of any of them. But yeah, I think this exercise is only on. I suppose I can check it, can't I? The planarity algorithm is not on the syllabus for AS. It's an AM thing. Yes, it's all critical. So there you go. You should all be able to do that.